Good afternoon, everyone, and thanks for coming along. And welcome to everybody watching online. Normal rules apply. If you've got a device, please put it on silent or off. The hashtag is TomorrowTech. And for anyone watching online, please do send in your questions using that hashtag, and I'll pick up on them later. There will be minimal tweeting from me today because, to be frankly honest with you, for someone like me who isn't an expert, tweeting quantum technology in 140-character sound bites is incredibly difficult. So anyone who is tweeting in the audience, I will retweet, and I'll be very, very grateful. So I want to introduce today's speaker. Simon is part of our Bio-Inspired Quantum Technologies research program, which is about, I think it's about 25 people across 5 different physics disciplines. So it's a fantastic interdisciplinary program that we're enormously proud of. It's right at the cutting edge of where we might find the foundations of quantum computing, and it's very exciting. Even though I struggle sometimes to understand it, it's an amazing program. So I hope you enjoy this introduction from Simon.
We do here. I should say straight away that my talk is at a very high level and very general. So it goes much more broadly than the specific work supported by the Martin School, and indeed more broadly than any work being done in Oxford. I'm trying to sort of give a top-down view of the whole, what is this quantum technology thing? However, I mention, I think 4 people specifically by name in my talk, and this is for this worldwide field that's been going for 30 years, and 3 of those 4 guys are from Oxford. And I should apologize for that. I'm not trying to create the impression that Oxford has created 75% of the field. It's simply that it so happens that the particular things I want to explain have brought those guys up. So without wasting any time, I have an enormous number of slides, but hopefully I can get through them all. What I want to talk about is, first I want to remind you, because I know I can see we have a very mixed audience here, what we mean by information when we speak about it from the point of view of any technology. And then, having thought about that for a few minutes, I'd like to introduce you to the quantum bit, or qubit. And then going on from that, I'd like to tell you about 3 different areas of quantum technology, which are all emerging, some of which are already in devices that you can buy. So this is quantum sensors, quantum communications, and then, for the largest segment of my talk, quantum computers. Quantum computers being my own particular focus and interest. And I want to tell you about the worldwide race that's going on to develop all these technologies, but in particular, the quantum computers. Please do, well, okay, I guess you better follow the normal protocol if there are questions. Normally at this point, I would say, please do shout out if you have a question. Whether or not that gets no, all right, I'm getting, so please don't shout out if you have a question. Okay, of course, of course. So we'll take questions at the end, I guess. Okay, so first off, the nature of information. So I think everyone in this room must be familiar with the sense that when people talk about information from a technology background, they are talking about zeros and ones. They're talking about binary. I'm just going to time myself. Okay, so what do we mean by that? What we mean is that the information in the traditional senses, which might be text, music, images, movies, can always be broken down into a stream of numbers if we wish to store or transmit or process that information. So pretty quickly, we come from general notions of information through to the idea that if we can store and process numbers, then we may be able to work with information. Now, numbers can be efficiently written in binary, which is just the number system you get if you only allow yourself 2 symbols, 0 and 1. Now, we might ask ourselves, we're not yet onto quantum computing and such things, just generally, if we want to imagine a machine that can process information for us, or just store information, or in any way manipulate information, what, based on these, just these 3 bullet points, what would be the way to build such a machine? Well, surely it would be to focus on creating a machine whose components can be in one of 2 different states. Because we know from those 2 different states we can represent any numbers, and from numbers we can represent any information. We could try and build a machine whose basic components are in, let's say, 10 different states, and then it would be nice and easy to represent the numbers 0 to 9, the digits. But that would be harder technologically, because we would demand some things about those components. In particular, they should be stable. And It's harder, of course, to make a system with more stable states than with fewer, and that leads us to basically the notion that we're going to make our machines out of components that just have two stable states. Now, here's a few examples from over the years of technologies or storage systems, if you like, that represent information in zeros and ones. This first one is punched tape, which stores programs and data by the presence or absence of a hole in an assigned position on a piece of tape. You then shine light through it, and the light gets converted to an electrical signal if it can get through. That's your 0 and 1. Here's something a little bit more contemporary. So this is a magnetic hard drive that many of us might still have in our computers. And if you zoom in to the surface of that magnetic hard drive, what you'll find is that there are little magnetic particles in regions. And if you go to one of those regions and make all the magnetic particles point to the left, then you say that you've stored a 0 there. On the other hand, if you make them all point to the right, then you say that you've stored a 1 there. So again, we can see that it's going to be, the simplest thing we can do is just to shoot for storing two different stable states. And then finally, this one here, an electronic circuit that is also capable of having two stable states, a so-called flip-flop circuit. So those are some things from conventional technology that store zeros and ones. One thing I'd like to point out to you just at this moment is that these are all quite robust, in the sense that you could damage them a little bit, mess around with them a little bit, and they would still be storing a 0 or a 1. You can see that more easily from the examples on the left. It's true of all of them. So if, for example, our punch tape gets a little bit worn, and so the holes are not quite perfectly circular anymore, that's still going to either transmit light or not. It's going to be okay. Similarly, perhaps most clearly with the magnetic disk here, if some of those little magnetic particles go and point in the wrong direction, but the clear majority is still pointing in the right direction, then again, we've still got our 0 and 1. We can come along and we can read it, and we could even rewrite that 0 or 1 in order to push everyone back into the correct direction. It's a robust way of storing information. And that's something we'll really struggle with on the quantum side when we come to it. Now, we are now in the middle of, or who knows whether we're at the middle or the end of where we are, but we're in a revolution in information technology. And when physicists see some kind of revolution like that, they're always fascinated to ask, what is the basic physics of what's going on when you really get down to it, when you really strip it down? And the first person I'm going to mention in this connection is an Oxford chap called David Deutsch, who in 1985 was asking himself this. But I'm going to simplify it down to, what is the basic physics of the bit? We've said that the bit, which is the object that can be 0 or 1, is absolutely fundamental to what we might choose to do with our information, how we might process it, and so on. So let's ask, what is the basic physics of the bit? All right, so I'll rephrase that question as what we say about a fundamental two-state system. What can physics tell us about that? So quantum physics is the basic theory that underpins all the matter systems and light that we use in our technology. So we better ask that question in the language of quantum physics if we want to be getting down to basics. Quantum physics is good at describing states, actually. We have the Schrödinger equation, which is to quantum theory what Einstein's equation is to relativity. It looks a little bit more messy, a little complicated, I guess, but it's really saying something quite simple. That psi object there that appears on both sides stands for the mathematics that represents our system, which might be an atom, for example. And then on the left, what that reads is the energy of that state. And on the right, how you read that is how the state changes. So this equation is really saying nothing more complicated than a state changes more rapidly, if you like, if it has more energy. The way a system changes depends on its energy, which I think is a fairly sensible notion, if you think about it. So it looks like a complicated mess of symbols, but it's really trying to say something fairly simple. But what do we get if we ask our question about a bit? So we can certainly ask what will it take to have two solutions, two different solutions to this equation that are stable. And then that would be our bit. That would be our basic physical two-state system, something that that satisfies this equation and has two stable states. All right, mathematicians in the audience note one thing about this equation. It's linear. We're going to come back to that in a minute. Don't worry if you don't know what that means. So here we go. Let's imagine a tiny magnet, just like this bar magnet here. Now really, if we drill down onto a magnet, sooner or later we'll come to the individual atoms. That doesn't actually stop us. An individual atom has a quantity called spin, which we will simply think of as being like a tiny bar magnet. Now, if we interrogate what the properties are using the Schrödinger equation, then we will find that the spin of an atom, that tiny magnet, has only two stable states when we put it in a magnetic field. By the way, this is the most technical part of the talk, so don't worry if you're finding it a little technical. If we imagine a bar magnet and we stick it in a field, quantum physics will tell us, if it is this elementary magnet, this basic atomic scale one, that there are only two stable states. That is what we call up, which you can simply think of as the North Pole pointing in the direction of the field, or down, which is the opposite. These are the two stable solutions. And that's great, because that's all we were asking for. So that is our bit. We can say, all right, it looks like an individual atom, in fact, not even the atom in general, just its magnetic quality, can be one of our basic bits. Fantastic, that all looks good. Let's just review its merits. So we'll call it a quantum bit, because we came to it by thinking about quantum physics. It has two distinct states, that was the point. By the way, we can also set the state of one of these tiny magnets, and we can manipulate it. I'm just going to assert that. That's good, because we're going to need that if we want to imagine storing and processing information. If we put it in state 0, and this is the crucial one, then our little atomic magnet will stay in state 0. And we can find it in state 0 later, which is exactly what we want from something that stores information for us. We don't want it to disappear. Similarly for state 1. So that all seems done. It looks like we're done. We've just discovered that, yeah, ultimately we could use individual atoms for storing bits. Maybe one day, computers will be like that. But this is where it gets a bit weird. Although we got to this conclusion by thinking about the Schrödinger equation, it has this property, which comes back to being linear. If you have two solutions of this equation, you are allowed to just add them up in the maths. And that's another legitimate solution, meaning another allowed state of reality. Now, the two that we had so far, I'll just flip back, were, oh gosh, it's a fair way back, were pretty sensible and down to earth. We can certainly imagine a magnet going that way or that way. Nice. But what does it mean to add them together? That seems to be an equally legitimate state of reality. We're allowed to add a magnet pointing up and a magnet pointing down, according to the Schrödinger equation. So this is this famous thing called a superposition. It is, in this case, two different states that we feel we can understand intuitively, but they're added together. And that doesn't sound like something that makes everyday sense. That is kind of mysterious. What is that trying to tell us about the universe, the fact that such a thing seems to be allowed? Before we get to that, we might ask, why don't we ever see these superpositions? If this is true, then why don't I see my Coke can in a superposition of empty and full? Why don't I see this happening around me? Well, there's more to quantum theory besides just the Schrödinger equation. We also need a mathematics of measurement, and there's a number of ways you can try and do this. But what it comes down to is that when a system is measured, it seems to, I use that word cautiously because different people like to think of this in different ways, collapse into one of its two stable states. So that language is perhaps not the preferred language, certainly not in Oxford, but it is informally what you can say, and what experimentalists working in this area would say is that when you look at a superposition, in the sense of measure it with some technology, then it will just choose to be one thing or the other. So our mysterious combination of up and down for our magnet will just choose to be one thing or the other if we measure it. Well, now, does that make everything sensible and intuitive again? Can we now just relax and just chill out? Because it seems that we're never allowed to see these superpositions, so what does it matter if they exist or not? Well, not really, because we still have to try and understand what the state of the system was before it was being measured. Now, the meaning of this, the sort of the intellectual challenge of understanding what it can mean for a physical thing to be two, what we would say, different things at the same time, has been debated for longer than you might think. The term qubit, it's a relatively new term from the last, certainly 30 years, but it's effectively exactly our old friend Schrödinger's cat, the cat that is famously dead and alive at the same time. In the language I'm using, I could cast this as a thought experiment between Schrödinger and Einstein when they were wrestling with the idea of superposition, and they thought about what if the qubit became a macroscopic object. even though the term qubit wasn't around at the time. They had a qubit in their experiment, which was a radioactive element, might or might not decay, essentially, and that just turned into the live and dead state of the cat. So this intriguing, concept of the qubit of superpositions has certainly been around for a long time, and academics can take it one of two ways. We can either ask, what does it all mean? What does it mean to live in a universe where apparently such things are possible? Does it mean that we need to actually think of reality as being multiple realities that have different states at the same time? That would be many worlds. Or are there other interpretations of the mathematics that can explain it for us? That's one way we can take it as academics. On the other hand, and for today's talk, we can take it more practically and say, given that this is true, math says it's true, every experiment ever done says that it's true, then can we harness it? Can we build technologies around this principle of superposition and other ideas like entanglement that I'll come on to in a minute? Can we build technologies around that? So in other words, can we harness the weirdness and make it work for us and perhaps do things that otherwise would be too hard or even impossible? Okay, so this is where I get into the technology side. So if you switched off for all that nonsense and didn't like the look of the Schrödinger equation, then please switch on again. All you need to take was that there's this concept that things can, that you can have a 0 and a 1, two different conditions of matter present at the same time. Now I'm going to talk about quantum sensors. I need to tell you this, that when a qubit is not in one of its two stable states and is instead in a superposition of them, then it is very, misspelling error there, but it's very sensitive to its environment. Now, what physicists mean by environment is not global warming and so on. They mean everything that is not the system that you're focusing on. So if we were focusing on one of our little atoms that is like a little magnet, then everything around that atom, the apparatus that's holding it in place and so on, is the environment. And the way that atom behaves when it's in one of these strange superpositions is extremely sensitive to the environment. That is bad news if we're going to try to do information processing with these little guys, because we don't want our information to be vulnerable to every little variation in the system around it. But we could turn that disadvantage or challenge into a merit by just looking it the other way around and saying, well, then wouldn't it make a smashing sensor? Because sensors are supposed to be strongly affected by the things around them. And maybe this is a route to an amazing new class of sensors, and it is. Okay, so let me pose a question to you. What gives pink diamonds their color? So my answer is optically active qubits. So this is a picture of, zoom in on diamond lattice. This is where the atoms go inside a piece of diamond. They're the gray ones for carbon. But you see there's a green chap there. That's a foreigner. That's a nitrogen atom that's in the diamond lattice as a stranger, as a impurity. And sitting next to it is a hole, a missing carbon atom. So we've got an extra atom and a missing atom. Now that little entity looks and behaves, in terms of its physics, a bit like an atom sitting in the middle of a vacuum. Because although it's held in place by the carbon atoms, the internal states of the nitrogen atom are not affected by the diamond. It's almost like an invisible scaffolding holding that extra atom in place. And that gives us a rather nice qubit, because as it turns out, we can play with the states associated with what's called an NV center. You'll see that a lot if you look in the literature of current technologies for quantum computing. NV, nitrogen vacancy center. So there's your nitrogen, there's your vacancy. That thing acts like a single atom or a single qubit held in place by an invisible scaffolding, as I say. What that means is you can start to build it into a technology. So here's a concept that's being aggressively developed by various groups around the world for a new kind of magnetic field sensor, one that would be sensitive even to the tiny magnetic fields emanated by individual molecules. So you have your piece of diamond, it comes down to a fine point, and in the point of that piece of diamond, which is the pale blue piece of my picture, you have one of these NV centers acting like a tiny magnet, which is a qubit and can be put into a superposition, in which case it's super sensitive to its environment. Here, the relevant environment is the magnetic fields coming off of that molecule beneath it that we're trying to understand. some biomolecule. Here it looks like the artist has taken DNA, but it could be anything. It could be some important protein associated with a virus that we're trying to understand. We've deposited that on a layer, and now we're probing it with our magnetic field sensor, able to actually identify the characteristics of that molecule right down there at that scale by having this exquisitely sensitive probe. And here's a second idea. I won't dwell on this because I'm aware of time passing. This is an idea of having a whole array of such sensors and allowing it to monitor, for example, a living neuron as it fires. Okay. So that was my very, very brief light touch on quantum sensors, the notion that because qubits are sensitive, you can turn them into a generation of sensor technologies. Let's get one step more ambitious and think about communication. So now we are moving back more rigorously into the domain of information. We're talking about transmitting information. More than ever, we care about the security of our data. I think every week there's a story in the media about data in some sense being compromised. Can we do anything about it by harnessing these strange phenomena that I've been talking about? Maybe this concept of superposition could help. Can we, in fact, enforce the security around protecting our data by the laws of physics, whereas at the moment, data security comes through using codes. So you encode, or your computer encodes your information and sends it over the internet. And you hope that there is no one who's got a powerful enough computer to crack that code, either because his computer's super powerful or because he's more clever at cracking codes than the guys who wrote the codes. Could we instead just discard all that and instead use physics to protect information? The answer is yes, in a couple of different ways, actually. So I should say first, how is it that eavesdroppers, let's focus on this problem. So suppose that what we're worried about is eavesdroppers being able to come up to the line that connects to legitimate people who are trying to communicate and just listen in on the line. How would you listen in on the line these days? Well, most communications on any significant distance are achieved now down fiber optics with pulses of light. It's in fact, as I gather from what I read and what experimentalists tell me, it's ridiculously easy to eavesdrop on conventional communications by light. What you do is, and it's in this little image here that you can see that's a rather simple looking gadget, it's all you need. You take the fiber that you would like to spy on, you strip off the cladding, and you bend it. You don't bend it enough to break it, because then everybody would know that it was broken. You bend it a little bit, and what happens is light, most of the light will go around the corner. So the light is flying down this fiber optic, which you can think of as a thin thread of glass-like material. So the light will zoom around the corner, but because you've bent it, a little bit of the light won't make it, and it will spill out the side of the fiber. What you do then is you put a little detector just there so that you can see some of that stolen light. And the guy at the other end, if you're careful and good and your equipment is high quality, the guy at the other end won't know it's happening because you've only taken a tiny fraction of the light that was going down there. And in that way, you're able to get a copy of everything that is being transmitted. So can we put a stop to that kind of thing using quantum physics? So in these stories, there's always three characters. There's Alice and there's Bob, who are usually the good guys. And then there's Eve, the eavesdropper, who is doing her best to monitor their communications. This is the language of cryptography since long before quantum computing. It's the challenge of two people communicating with complete privacy. Can we put a stop to Eve being able to eavesdrop? What we can do is we send qubits, not bits. So we send, for example, individual particles of light, individual photons. That's one kind of qubit, in fact. Rather than huge pulses of light, we send individual photons, and we exploit the fact that Eve cannot now measure that light without disturbing it. This is the opening the box, the determining whether the cat is dead or alive, but now mapped onto a photon, so that we will, even if we manage to measure the photon without destroying it, we will cause it to collapse to one option or the other. And in fact, using the right protocol, Alice and Bob can tell that this is happening. They can tell that there's interference on the line, not by, as in the sort of classical scenario, just having a super sensitive measure of whether any light's gone missing. Even if no light has gone missing, they will tell that there's been this interference by the very fact that quantum physics demands that measurement causes consequences to the object being measured. So by switching over to using qubits instead of bits, physics forbids Eve from being able to monitor the channel without being caught. And by the way, that is available now, not from me, from companies like ID Quantique. This works and can be done. But what I'm going to tell you a little bit more about, as quickly as I can, is something even more powerful than the current, let me flip back, that was too much, even more powerful than what you've just heard about. What you just heard about was Alice talking to Bob down a line that can't be compromised. But if you think about the internet, for example, it's not made out of Alice talking to Bob. It's made of a whole mass of people, all connected to each other, and people talking to one another through multiple intermediaries. What can we say about that? So let's strip that problem down and say, could Alice talk to Charlie using the services of Bob as a kind of relay and, if necessary, boosting and improving the signal, even if Bob now might be doing something naughty? Bob might be an adversary. He might wish to eavesdrop on the communication. Could we possibly think of a way to make even that work? And what I can assert for you, and I'll tell you more if someone chooses to ask me a question, is that even this is possible, that Alice can communicate to Charlie, in fact, through any number of intermediaries, and those intermediaries cannot eavesdrop and cannot prevent Alice and Charlie from sharing complete privacy. All that they could do is denial of service. Bob could just switch his gadget off. Of course, that's going to be the case. But in a network, of course, there's usually multiple routes. So even that isn't going to stop Alice and Charlie having privacy and being able to communicate. OK, so sorry, my slide's a little bit screwed up there. So I won't dwell on this because I need to get on to quantum computing, which is what I'm longing to tell you guys about. But this is an amazing thing if you think about it. I'm saying now that two guys who are part of a network can communicate over that network without using codes and without trusting the other people who are running the network. If they get what appears to them to be a good, secure channel between them, then it is. And there's no way for the guys on the network to be finding out anything about the communication they have. So this was an idea due to Artur Ekert, who at the time was working in Oxford and is now an Oxford professor, Ekert-style cryptography. And in order for me to take you through it, I'm going to have to tell you two things. Something called the one-time pad, and that's an old idea that predates quantum technology, and quantum entanglement, which is the other thing apart from quantum superposition that always gets mentioned in the context of quantum technology. People always talk about entanglement. It's time for us to meet entanglement. But first, the one-time pad. So this is a solution that would work in the 1800s or whenever you want to imagine yourself. Doesn't need any advanced technology. You and your partner have traveled far apart, and you wish to be able to communicate with complete security. Before you parted, you each took a copy of what we will call the pad. It's a long list of random symbols. You and your partner cook them up randomly, maybe by rolling dice and writing them down. You've got two perfect copies. So if you've got a certain symbol in a certain entry, so has your partner. What do you want to do when it's time to communicate? What you do, you can send an absolutely secure message just by combining each letter of your message that you want to send. So I might be sending a message that says, I don't know, attack France. I don't know why. I don't dislike the French. But if that were my message, then the first letter is A. So I turn that into a number. Maybe in my scheme, A is 65. That's not secret yet. That could be a well-known scheme. But now I take one of my numbers from my secret pad and I add it on. And now that gives me a new number. And I can send that number openly. It doesn't matter who's eavesdropping, listening. I don't care. Because they can't work backwards to know what the number I started with was unless they know what I added on so that they can take it off. And only my partner has that information in her pad. Only Alice knows that. And this is perfect. It's what's called information theoretically secure. That means there is no information to be gleaned from the message to an eavesdropper. Because of this random number having been added on that they don't know, they cannot reverse engineer it with any amount of computing power. It's just not there for them if they don't have that missing piece of information. The only bad thing about this is that I have to use each symbol only once if I want to be safe. So I use that random number, which might be like the first one on page 57, and then I cross it off and I go to the next one. So you can see that I'll consume this pad over time. That even though I may have shared a lot of information, over time as I send messages over the distance by using these, locking the message, if you like, with these numbers, I'll be crossing them off, and eventually I'll get to the end of my pad. That's it. I can't do it anymore. And of course, the other downside is that I had to originally meet with the person I want to communicate with in order to share this crucial resource. So wouldn't it be fantastic if we could do all this, but by a method that would allow us to generate this secret randomness at a distance without meeting up. And then we could replenish the randomness. Whenever we wanted to send a message, we could just get some randomness, magically obtain 2 of these matched little books of random numbers, use them to protect our message, send our message openly. The book would never run out. It could be replenished. Can we do that? We can't do that with conventional physics. We can do it with quantum physics. So now it's time to introduce quantum entanglement. I don't know, I expect we have some German speakers in the audience. I can't really pronounce this, but this is what Einstein referred to entanglement as, which is usually translated as spooky. Spukhafte? Would anyone like to have a go? Roughly, right? Okay, so quantum entanglement was the one that was so weird, and remember this is the guy who was talking to Schrödinger about Schrödinger's cat. This is the one that's so weird that it gets to be called spooky. Okay, so we've already met the idea that a qubit can be both 0 and 1 at the same time. Well then, clearly 2 qubits, one that I have here and one that I prepared over here, could be both in 0 and 1 at the same time, each individually and separately. That's not very mysterious, that's just having 2 of this weird thing. Now, another way to think of that is that both qubits are in 0, or both of them are in 1, or the left one is in 0 and the right one is in 1, or vice versa. So in a way, there's 4 different possibilities in reality there, because we've got 2 of these weird things that are each in a superposition. Nothing really that I've added to the story of superposition so far, except that the Schrödinger equation will accept not only the things on those former 3 lines, but also this guy highlighted in blue. We don't have to have all those possibilities. We could just have a superposition of both of them being in state 0 and both of them being in state 1. The reason that's weird is because it's now no longer a good question to ask what is the state of Alice's qubit. If Alice has got 1 and Bob has got the other, it's no longer valid to say what is the state of Alice's qubit. You cannot answer that as an isolated question. It must be answered by referring to both objects at once. In a sense, these 2 qubits are now part of the same object in terms of this strange correlation that they have. They're both 0 or they're both 1. I can't say that Alice's qubit is in a superposition of 0 plus 1 and Bob's is separately, because if that was true, we'd also have these left-right, right-left combos. So this is entanglement. This is an entangled state. Now, if let's say I'm Bob, so if I measure a 0 on my qubit, then it must be that when Alice looks at hers, she'll see a 0 as well, because by looking, I've collapsed the superposition to the left-hand side of this. On the other hand, if I look and see 1, it's going to be random, but then I know that Alice will have also seen a 1. But this is it. It's random which one will happen. And there's another property that I must just mention to you. The last thing we need to know is something, a wonderful thing, called monogamy of entanglement. So qubits, if they are if Alice is Bob, excuse me, if Alice is qubit, I was going to get even weirder, right? If Alice is Bob. No, not that. So if Alice's qubit is entangled with Bob's in the way that we've written down here, it cannot be entangled with anything else in the universe, not if it's in this state. Entanglement, full entanglement, is something that can be shared only between one qubit and one other qubit. That is actually not a very difficult result to prove, and it's very important because it's what's going to protect our information transfer. So here goes Ekert's protocol. We're going to have a wire that connects 2 people and can allow us to send these qubits. What we'll do is, for simplicity, we'll say Bob will prepare this state in his lab from 2 qubits. He'll make this state using his equipment or his device, and then he'll take one of them and send it, oh, did I say Bob right then? So then he'll send it back to Alice. So now Alice and Bob share this state. They can test, there's a slip here in that I missed one important stage. They share their entangled pair of qubits, and they just store those. They put them in as it were, in the cupboard, and they share another pair and another pair until they've got a bunch of these entangled pairs shared between them. Now what they do is they sacrifice some of those by just testing that they are entangled. And physicists have thought for a very long time about having extremely rigorous tests that entanglement exists. It's motivated even at the philosophical level by saying, I don't like this thing, entanglement, I don't believe it, prove to me that it exists. And there's something called a Bell test, which I won't go into, which is, as it were, the rigorous test that entanglement is a real thing and is present with 2 particles. Testing them destroys them, unfortunately. But that's why Alice and Bob distribute a bunch of these, and then they randomly choose some and test them to check that they're still entangled. If they are, then those guys were not nobody had tried to entangle them with anything else in the universe, or else those tests would have been failed. So now they can take the remaining ones with confidence, having sampled and checked, sacrificing some of them, and use them just to generate this one-time pad. They just measure, and they know that their results are correlated, but that no one else could have introduced another qubit correlated with theirs because of monogamy of entanglement. Okay, so this is really a stunning thing. So again, if I've lost you a little bit, let me bring you back. This is a remarkable thing because it allows the concept of communication purely protected by the laws of physics. And as I say, although I haven't entirely explained this, through monogamy of entanglement, even you can go through intermediaries and they can do nothing to couple themselves into the process. So what you end up with is a scenario where people can communicate with each other by an unbreakable form of cryptography, which is based purely on quantum physics. So I think that's an exciting possibility. It's I don't even know if it's a good thing, right? It might be too much cryptography. Do we want people? There's no way that law enforcement can break in on this, because you can have a complete copy of the message that's been transmitted, but it's been locked by these random zeros and ones that only Alice and Bob know. So it doesn't matter if you have an infinitely powerful computer or the most clever mathematicians in the world, you cannot in any way break into this. And that may be more than we should let people have. It's an interesting social question. But I don't try to answer that. I'm just throwing out there that it's something we can do, and in the relatively near future, by the way. You can't buy this yet, but 5 years maybe you will be able to buy this. All right. On to computing in the last part of my talk, and let me assess how much time I've got. Okay, I think I have enough. Right, I'm going to tell you about quantum computing, and I'm going to use a couple of phrases that I'll try to explain, which are the ones that excite physicists about this kind of quantum computer versus other exciting machines like the D-Wave machine. I'm not going to talk about that in my talk, but I'm happy to answer questions about it. But the one I'm going to tell you about is what's called a fault-tolerant universal quantum computer. Now, I better say what the word universal is, because I'm not sure it comes up in a later slide for me to remember. This is a universal computer, this laptop. What that means is it can do anything that a conventional computer can do. When this computer was built by Apple, maybe there are some games I want to play or some software I want to use that wasn't even written. But it will run on this because this is a universal computer. So using a suitable language, a guy can invent a task for it and run it on it, and he didn't even, that wasn't even known about when the hardware engineer built the machine. It's able to adapt itself to different tasks with complete generality. It is a universal machine. That's one of the properties that we would like to have from our dream quantum computer, of course. We want it to be the case that once it's built, anyone who can think of a program to run on it will be able to do so. Fault tolerance, I may say a little bit more about, in fact, I am going to say more about, so I'll hold that thought. But before I get into computing in any depth, let me just motivate why we might even need a more powerful computer. I mean, heck, aren't computers powerful enough already? It's like barely a week goes by that we don't read about some new feat that has been achieved by computers. I think it was last week, possibly the week before, that people working with Google managed to use the technique called deep learning to build a machine that could beat experts at the game called Go, which is a board game widely considered to be much tougher for computers than chess. And we all remember when Kasparov lost to Deep Blue, I think it was. So these are feats that we might think of as intellectual feats by big computers, and there are many other things. So why do we want computers that are fundamentally more powerful? Surely they're powerful enough. Well, no, because certain kinds of tasks are so difficult that they go beyond the capabilities of any conceivable conventional computer. What I'm throwing up here on the board, if you can blur your eyes a little bit, you might see the continental United States emerging from this squiggly wiggly line. There are dots along this line, if you can see it, and those dots represent cities. So what this is a solution to a famous problem in computer science called traveling salesman, which is generally the problem of someone gives you some cities, locations on a map, and roads, and your challenge is to get around all the cities in the shortest possible total route, because you're paying for petrol, and you are a salesman. So you want to get around all these locations. How are you going to do that? Well, you want to just figure it out. So if I gave you 4 cities, you would be able to do that with a pencil. You'd convince yourself you'd found the shortest route with a pencil. If I gave you 20 cities, you could do it on a computer. But as the number of cities grows, multiplicatively, the number of possible routes grows. so that when you add your 100th city, there are now 100 times as many routes as there were, possible routes, when there were only 99 cities. And this explodes out of control for any machine, even a supercomputer. Okay, so that's one example of a task that we would love to be able to get better at. Now, the first indications that there might be something exciting to the notion of putting a qubit or a bunch of qubits into a machine and calling it a computer came from David Deutsch in '85. He found an example of a problem that a quantum machine could do in fewer steps than a conventional one. It was a very limited, very specialized example, but it was tantalizing because it said, look, here's something that a quantum machine can do that's different. And then in '92, working with Jose, Deutsch and Jose generalized that to a more dramatic example that really showed a clear difference for a machine of any size between a quantum version and the conventional kind. But these were still artificial problems that were not of general use. And then came the famous discovery by Peter Shaw in this, coming out between '94 and '96. He showed, on paper of course, because no machine even now exists that can do this, that a quantum computer with these qubits inside it would be able to perform a task called factoring, which is tough, one of these things that are tough for conventional computers. Factoring just means I give you a big number, and you tell me if there are two numbers multiplied together that will make the big number. So I could give you 15, which isn't a big number, but you would immediately say to me, that's 5 times 3. You factored 15. But if we consider the task of factoring ever bigger numbers, basically to find out if they're prime or not, and if not, what the factors are, that becomes it's one of these exploding problems, because as the number of digits increases, the amount of checking or analysis that you have to do explodes exponentially, and you won't be able to find those factors. Shaw showed that a quantum machine using these qubits, which can be in multiple different states at once, would be able to perform factoring efficiently. And that was a tremendous result, and disruptive and worrying even, because the impossibility of factoring big numbers, the practical impossibility of it, is what defends our conventional codes that, for example, allow transactions over the internet to happen safely. So what this means is that a quantum computer could be an amazing code breaker, a disruptive, dangerous machine, really, in that it could unlock the most common codes that are used around the world. But that's very tantalizing because it shows you something the quantum computer can do. Now, if we're saying we're thinking about a radical new exploratory technology, which, among other things, is a great code breaker, this may sound familiar to you, especially if you watched, what's this film called? It's gone out of my head. Anyone? The Imitation Game. Yes, exactly. Because it's like, I don't understand the title, basically. That's why it went out of my head. But so that Turing and his team put together one of the early computers precisely for this kind of task. And now we're saying that quantum computers would be on another level when it comes to cryptanalysis. Okay, but is it a realistic possibility? If so, when will we see one? Why is it that the dates that you've just seen me mention, which were in the 90s, early mid-90s, or indeed earlier than that, why is it we don't have one already? In the time since people have been, here, 95, let's say, we had the factoring algorithm, why haven't we now got a quantum computer? In that period of time, after all, we have had iPhones invented, and they've gone through, 5 revisions, I guess. So why haven't we got a quantum computer? What are the physicists up to that they haven't managed to get one out here yet, right? Because it's hard, is the dumb answer. But let me show you a little bit why it's hard, and why now I'm really optimistic, and I'm comfortable getting on board with a lot of programs, and show you one in a bit, which are pushing hard towards a real deployable technology, whereas if it had been done even 3 years ago, it would be premature. The problem is one of controlling imperfection. A quantum computer must work with qubits that are in superpositions, but we've already seen in the sensor example that these superposition objects are terribly delicate. And that's a heck of a problem, because you're trying to hold in place the components of your technology, but they're vulnerable even to slight fluctuations in the devices that are holding them. They're vulnerable to the rest of the machine, let alone the rest of the universe. They are tricky, tricky fellows to deal with. Okay, so we've met the idea that the environment is everything except the system. In a conventional system, we can check at any time to see if our data seems to be degrading or if it's gone a little bit wrong and fix it. But we're not allowed to just naively come in and look at the memory of our quantum computer, because if we look at it, it will collapse. Frustrating, right? We know after a certain number of operations that things won't be perfect, because technology is never perfect, but we're not allowed to check it. At least it seemed not. So that was thought to be, by many serious guys, a showstopper. That was thought to be the end of the road for quantum computing, because however well you build the machine, for sure it will have little imperfections, and over time they'll add up, because you're not allowed to look and see if it has or not. I just have to pause for 1 minute and show you this. Would anyone like to guess what this is a picture of? The analytic, someone knows the answer, right, because that came with some confidence. That's Babbage's analytical engine, even the correct thing, right? So this is, some would say, the first computer that was put down on paper. It's a programmable computer that works through the technology of the 1940s, i.e. cogs. So it's a beautiful design, and basically it's a correct design. It should work in the sense that on paper the ideas are all there. It's a programmable thing that can manipulate numbers as a computer does. There's a word written in the middle there that you won't be able to read called the mill, which is what his word for the CPU, the processor at the core of the thing. But even though his ideas were correct, he didn't get it to work, because the imperfections in a system like that, of such fearsome complexity, so many components, overwhelmed it. He didn't have a theory, an analysis that could show him how perfect the components would need to be in order for the whole object to work. And in fact, the best techniques of the time could not produce components that were sufficiently perfect, and it failed. So what we might worry is that quantum computers are in the same category. We can dream of these devices and draw pictures of them, but if we can't handle the little imperfections, they will add up and stop it from working. So that's why people thought it was a showstopper. They thought that quantum computers, a nice idea for theorists to wonder about, would go the same way, essentially, as the Babbage analytical engine, and would not be achievable. Okay, but that isn't the case. So around the same time as the Shor algorithm, the same chap, Peter Shor, and also Andy Steen here in Oxford, found a way around this problem. That yes, the computer's making small errors when in its internal state, and we're not allowed to look at the qubits, but still we can fix them. He worked out how to do this. The trick is to have a separate little calculation, essentially, that computes whether there have been any errors, and the answer goes on to some other qubits, and those ones you are allowed to look at. And looking at them only collapses the question, are there errors or not? And you want that to resolve itself, and then you can fix the errors. So an elegant and really, in hindsight, simple solution to what looks like a fundamental problem. Now, Andrew and Peter are theorists. They had these nice ideas, and then they wrote them down, and then they did some analysis, and they said, look, I figured out now that I can make a quantum computer behave itself, even if it's making small imperfections. I found out how to monitor it and put it back on track. But clearly, that's going to have some kind of limits. If the quantum computer is making frequent errors, then even the little calculation that's supposed to check for errors will go wrong itself. So there must be limits to this. There must be a number that says, if the computer is better than this number, more precise, more high fidelity, we would say in the field, then things are good. And I'm going to be able to stay on top of errors, notice them when they happen, fix them. On the other hand, if the computer is worse than that, lower fidelity, if it makes errors at a faster rate, my idea isn't going to work, and things are going to spiral out of control. That's nowadays called the threshold for fault-tolerant, so being able to tolerate faults, quantum computing. Now, where did things look when these theories came out? So, excuse me, how did the scene look when this first came out? So we would say that the theorists said, look, if you can just build me a machine with the rate at which errors happen, in other words, the chances that something goes wrong when I ask for a particular process to happen inside my machine is 0.0001%, a small chance of an error. By the way, conventional machines are much more reliable even than that, but quantum qubits are tricky, so that's what they were asking for. In the lab, variety of different numbers, of course, depending which lab and what they were trying to do. Fair to say, though, that the harder operations that they needed to get the hang of in the lab, in prototype devices, were at 10% error rates. So that's an enormous gap between a 10% error rate that the hardware guys can do and a 0.001% error rate that the guys designing the procedures. Now, you can look at a chasm as big as that and take a variety of attitudes depending on whether you're an optimist or a pessimist, right? How long will it take to close a performance gap of that factor? You might say a few years. If you're a super optimist, you're like, yeah, no, it's amazing, we're making rapid progress. Many decades, or never. It would be legitimate to say, this is a gap that cannot be closed, it's just too hard. Well, how do things look now? What's happened in the intervening periods, those essentially 20 years, is that theorists have managed to improve the ideas, going forward from what Peter and Andy provided us with, improve those ideas and make them more permissive of errors. So that number has improved, and of course, at the same time, the experimentalists have been getting better and better at controlling the systems in the lab. They've been making progress. So where are we now? And actually, these slides I made 18 months ago, this one slide. So it's not even where we are now. It's like where we were like 12 months ago. All right. We are now there, okay? That's why I'm optimistic, because the capacities in the prototypes in the lab are now at error rates that are far below 1%. About 0.1% is the best number, a world record, which, by the way, is held here in Oxford for a technology called an ion trap. On the other hand, the theory schemes now say that they can handle up to 1% errors. So we've got the chasm closed, and that's why it's a time for optimism and trying to now really forge forward. We no longer have this difficult failure to connect that is an impediment. All right, so apparently the answer in this case to how long it takes to close that gap is 2 decades. All right, so those numbers, though, are for prototypes in the middle of a big messy lab with loads of cables all over the place. How long will it take before something like this can now actually be taken out of the lab and we might see something that really solves real-world problems? Okay, so I'm going to briefly now flick through a few slides that tell you about how the race to build these machines is hotting up. And by the way, in this race also is the race to bring out these communication technologies that I've mentioned and these sensors and so on, but focusing on the computing side. Okay, so the race is on. New money. So in 2013, the Chancellor, at the end of the year, announced 270 million to invest in quantum technologies. I believe it was actually announced in the form of a tweet. So we were all, extremely excited to see the details that were beyond the 140 characters or whatever. And we wanted to see how much of this money would be money that, as academics work in these areas, we could go for if we were passionate about making technologies real. And when the details became more clear, it turned out that it was 80 million plus 75 million, 155 million, for an investment into an initiative led by universities to try and accelerate progress in the UK towards these kind of things. Okay, so this slide is a little bit out of date. It says competition is still ongoing. It's not. So at the end of 2014, the outcome was, I'll skip through this, was announced. And the bottom line is that there were 4 centers chosen to push forward technology. And Oxford was one of the centers, or I should say the entire entity is called a hub, and Oxford was leading a group of 9 universities, as shown in this diagram, all pushing towards the kind of things I've been talking to you about, especially the quantum computing side of things. And so we have about 40 million plus a significant amount of industry investment to try and just go faster and make these things happen, make them leave the laboratory as soon as possible. Here's a few of our industry investors. We have more investors than these, but those are the ones that I can lay my hands on their logos quickly. We're already, scarily, more than a year in. So it's going pretty well, but it's a very, very ambitious vision. And what are we going to do with the money? What are we doing with it? This is a picture, which I can talk more about if I have a question on it, for the kind of quantum computer we want to build. What I'd like you to take from this picture is just that it looks like a bunch of little boxes that are wired up somehow. And that is indeed our approach. We're trying to build small quantum computers, so small that they don't do anything interesting in of themselves, and wire them up in a clever way using light. And we want to do it this way because we know we can build those small guys, and we know we can do the wiring. And so it becomes an engineering problem to make the big guy. And also because I think you can see this is inherently scalable. If you can build this and make it run and be sufficiently well behaved and so on, there's no reason that you shouldn't plug more guys in. It's just a repeating pattern. This is the kind of thing we're trying to create. We call it Q2020 because it's coming up to the year 2020, so it was cute to focus on the fact that what we want is 20 of these little boxes, each containing 20 qubits, all wired up and jointly forming a 400-qubit machine, which, by the way, is easily big enough to go, well, the best conventional supercomputers in the world, if you ask them to behave like a quantum computer and predict it, can get up to about 40 qubits. Maybe if you pulled out all the stops, you could get to 50, like a big worldwide effort. But this thing's got 400 of them. Now, that's, by the way, on a curve so that my laptop can do 25 qubits. The machines we have here in Oxford, we're just actually writing some software that will allow them to do 35 qubits, and then a massive worldwide effort could perhaps do 50. We're on this kind of curve. So 400 is ridiculously beyond the reach of any conceivable conventional computer. But that doesn't, so I'll skip through a few slides here. Let me show you this. This is a picture of the kind of prototypes that we're working with here in Oxford. It's called an ion trap. It's actually a very, you can see the scale of it with the naked eye. This is about the size of, I guess, your little fingernail. And it's designed for trapping individual atoms and holding them in a vacuum. And each of those individual atoms is one of our qubits. Here it is mounted inside. So I don't know if this is an Oxford picture or one from our collaborators in Sussex, but what's happened here is the little quantum computer prototype has been mounted into a vacuum system because we don't want any other atoms, just the atoms that are holding our information. We don't want any other ones straying around. Now, what will it be good for? Let me just wrap up by saying this. So not the long-term machine. The long-term machine is a universal computer. Anything that we can think to try on a quantum computer, it would be able to do. But Q2020 isn't big enough to do that. It's a first effort. It will have 400 qubits perhaps, but that isn't enough to do everything you might conceive of. For example, it's not enough to do fault-tolerant factoring. But what might it be useful for? So we intend to use it for two things. One, demonstrating that it is the right architecture for building a genuinely huge-scale thing. So we want to build this little, as it were, piece of a full-scale quantum computer and show that we've got it operating at these far sub 1% error rates so that we can basically say, right, we've done it at this scale, it all works, this is a working component, let's now push for the big machine that would probably fill a room at least this size. That's task A. But we're also, and this is a really exciting thing for theorists right now in the field, is to try and spot useful things that this machine would be able to do straight away, not as a demonstrator of a future even bigger thing, but right now. And there are possible tasks in predicting chemical reactions, predicting the properties of new materials, or in this exciting area called machine learning, which is this one that conventional machines just beat humans at Go at. There are problems there that even this, as it were, little first generation, or as it were, 0th generation computer may already be better at than conventional machines, just with 400 qubits. Bear in mind that this thing has 16 gigabytes or something like that of bits. So we're saying that even with that, and much larger machines can't predict the behavior of more than about 30-ish qubits. We've got 400 of them. We're looking for things that we can do with that machine. A machine that one day had thousands or indeed millions of qubits, we know right now what we could do with it because we could do these full fault-tolerant procedures and it would be completely stable. This early guy is not going to be immune to errors. It is not going to be big enough to do general-purpose things, but it is already big enough to be impossible to simulate with conventional technologies. So we're very optimistic there's going to be a lot of juicy things that we can put the machine to work on, if indeed we can build it. So I think maybe that's a nice point to leave it at. So that was just my final slide, really, where I'm summarizing some of the different things that we might be able to do with this machine. There we are. I'll leave it there.
We have got time for questions. If you could wait for the microphone to reach you before you ask your question, because this is being live broadcast, and obviously it is being live broadcast, so if you don't want to be on camera or your voice recorded, then get one of your friends to ask the question for you. So we'll start near you, Claire, and then we'll come over here. So these two and here.
I didn't understand the Ekert contribution. Can you walk us through it?
Yeah, I can.
Alice and we've got Bob, and they have
That's right.
cupboards full of entangled stuff. Okay?
Yes, exactly so.
And somehow Alice wants to send Bob a message.
Yep.
But he doesn't know to expect a message, and he doesn't know which of his entangled things to examine.
So let me stop you there, because
a one-time pad would play some role.
yeah. So I can see where I lost you. So let me. I don't think I really need the pictures, but I'll go back to them anyway because it will help me. So yes, you're quite right that we've got Alice and Bob, and they would like to communicate with each other. And the underlying notion is going to be one of using a one-time pad. So you're right about that. So Alice and Bob have this quantum wire between them. They openly announce to one another and to the rest of the world, because they don't care, that they now want to talk to each other. Okay? So they now start sending Alice, perhaps if she's generating these entangled pairs, she generates a pair, sends one to Bob. He can openly say, I've got that, and then so on. So openly sending these pairs of qubit, or sending one half of a pair of qubit, until Alice and Bob have got, let's say, 100 entangled pairs between them. All of this in the open. And then they need to check whether they are, in fact, still high-quality entangled pairs, because the act of an eavesdropper would have been to degrade that entanglement. That's the monogamy of entanglement thing. If an eavesdropper tries to get in on the act of this, because she's in the middle, she might try and bring her own qubit and couple it in to the relationship between Alice and Bob's qubits. If she does, the consequences of that act will be detectable, and Alice and Bob will sacrifice some percentage of their qubits openly, so they can openly announce even that. So they measure some percentage of them performing this thing called a Bell test, which has been very rigorously worked out as a legitimate test of entanglement. If they're good with that, if they're not happy at this stage, if they feel the quality of the entanglement is too low, all they can do is just try again through a different route, or it's essentially that has failed. But if they're happy, because they randomly chose to sacrifice some of their qubits after they received them, those are a fair measure of the quality of the remaining ones that haven't been sacrificed. And now they just start measuring those. I'm simplifying a little bit, but they measure those, and they know that they're going to be correlated with one another. When Alice sees a 0, Bob knows that he will see a 0. When Alice sees a 1, he knows that she'll see a 1, and so they just measure them, but they don't. This is where they now don't communicate openly. They just write down the results. They've now generated some fresh one-time pad, which they can use however they wish, basically to encrypt as a conventional classical guy might from the 1800s, to just encrypt a message that, again, they can send openly. But because only they have this one-time pad, only they can make sense of the openly transmitted message.
Could you pass the mic down to...
Thank you for the very interesting talk. I have 2 questions, but they're both very short, so I hope they can...
Well, we'll see how we go.
At this stage, what's the main engineering challenge that keeps you from making
You think that's a short question?
Well, depends on whether you want to answer.
Yeah, I mean, okay, but let me have a go at that. Or just tell me the other one, and I'll see what I can get to it.
For a fault-proof quantum computer, what would be the percentage of qubits you would need for the fault correction?
Okay, that's an amazing question, so I will definitely have to answer that. So the first one, what are the engineering challenges? Well, all sorts of challenge. What we've got in the lab is a gadget that has high enough performance, thus proving that it's not against physics for us to have achieved it. What we have to do now is turn that into something that can be repeatedly created and made into a reliable, scalable structure. But I guess if I had to say one thing about what we want to do, I would say that we need to demonstrate and get good enough control of the optical linkage between the ion traps. Again, this is something that has been done. It's been done by a guy called Chris Monroe in the States, for example. But we need to get that working here with our kind of ion traps and get it working well enough for our purposes. It's tough. It's interesting, though, because it involves combining some guys that wouldn't have previously worked with each other, namely the ion trap guys, which know all about trapping and messing with atoms, and the optics guys, who know all about messing around with photons. Those guys now coming together to build this hybrid thing. Now, the other thing you said is, what's the number of qubits you need for fault tolerance? Now, this is why this machine I showed you with 400 qubits, I said it's not big enough to do fault-tolerant quantum computing. You might think, why not? What if I have what do I need to do? Do I need to, if I want to do an algorithm, the guy who's written the program, it's a story about 100 qubits. Surely maybe if I have 200 qubits, now it can, those extra ones can handle the fault tolerance for me. No, it's actually a much worse number than that. So this is the problem with building fault-tolerant machines and why they need to be a little bit further in the future. The factor is something between hundreds and 1,000 in scale-up. So for each qubit that you want to be able to have in your program, you're the high-level programming guy who doesn't want to know how the engineering works. The guy who's actually built the machine, the engineer who's like built it and worked out how the low-level components, he has to have something like 1,000 physical qubits for every one qubit that the programmer. That's if we're doing this fault-tolerant picture. The upside is that machine is now essentially immune to faults. The errors that happen at the low level get fixed, and they never happen to the logical ones, which is probably.
Okay, thank you very much. That's a very interesting talk. So I also have a question regarding these Ekert's cryptography.
Okay.
So, or two questions actually that are related. So, as I understood you, there's another technology which you talked about previously, where you talked about, well, where it would be actually possible to eavesdrop, but where, well, Alice and Bob would then figure out that they were being eavesdropped.
Can I stop you? Because I understand your question, but so there is a small misunderstanding there, as I guess I went very quickly through this. I did mention that there are two things, and actually that one of them is purchasable now, right? And then there's the other one that I told you about that's a few years away from being a deployable thing. But it's not that, so what's the difference? They both guarantee you that an eavesdropper can't eavesdrop without detection, okay? The difference is, so I kind of tried to explain this, but I guess I probably went a bit too fast. The difference is when you go from envisaging just a person trying to talk to another person down a dedicated wire that you might have, let's say, between two branches of a bank in a city or something like that, within the same city, and try instead to go to the vision of a network, where now, like the internet, if I talk to some server in America, I don't have a dedicated line, and it would be insane to try and have a dedicated line to everyone I might want to talk to in the internet. Instead, I rely on my information being relayed through the network. So now I'm saying that the advantage of the Ekert-style crypto is that we can use intermediaries, like in this picture, this guy Bob is providing the service of connecting Alice and Charlie, and they don't need to trust Bob. Bob can be someone who would love to eavesdrop on their message, and he still can't, even though he's now allowed to handle the qubits. So that is the difference, and it comes from this monogamy of entanglement, because however it's been achieved, even if Alice and Charlie bought their qubits from a really dodgy salesman who just comes up to the door and gives them some qubits, right? What they'll do is they'll randomly test some of them. If those pass the test for being high quality entangled qubits, then because it was a random sample, they know that that's typical of all of them, and now they can just go ahead and use them. They don't need to know how the qubits were distributed. They don't need any promises on the behavior of anyone in the network. And that's what's so powerful about it. There's no way to come in there and, like law enforcement can't rock up to Bob and say, here's a warrant, I demand that you let me into the information. It can't be done. All that Bob can do is switch off his system, but then a network will route around that.
Exactly, that was my second question actually. You said regarding the law enforcement, and you said that, well, you didn't want to comment on the question whether this was a good thing, that's a social or political question. But is there even any way for politicians to stop this? Once this technology
Okay, so that is a very good question. The answer is basically yes, but I'm not going to go into it. There's a way that you can deploy even this rich, untrusted node crypto, this ultimate cryptography, but in such a way that if you are the guy deploying it or the government that's licensing the technology to come out, that you can build in a capacity to essentially have a backdoor even on this. So it depends how it's deployed, essentially. But it isn't all or nothing. It isn't the case that you either go for this and then suddenly everyone can talk to everyone else in an unbreakable way, or else you just refuse to deploy it because you say it's too dangerous. There is an intelligent middle ground which a government could do. I could explain that. I haven't seen it written down, but it's kind of obvious once you understand the full story of the protocol.
I'd like to make a question about the quantum entanglement. If I influence one of the qubits, is that influence seen on the other one? And if so, can that be used for straight-on communication and maybe faster than light?
It's a good question. It's a question that we all ask ourselves in the field when we first hear about entanglement. It sounds like a way to do instantaneous communication. And when we say that the entangled objects can be as far apart as you like planets orbiting different stars, if you want, that sounds wonderful. In fact, you cannot communicate with them, and there is no meaningful sense in which influencing one of them directly influences the other. It can have consequences about the correlations between them, but Alice and Bob, if these are still our actors in the story, will only be able to use that information if they add to it some classical information about what they've seen, and that would have to just travel at less than the speed of light. So unfortunately, it isn't a way to get around relativity.
I know you mentioned the D-wave system just
Yeah.
briefly. I believe I heard that they're doing something with supercooling in order to maybe affect
right.
the stability. Can you comment
So maybe
on
I'll take that as a question, just what about D-wave? So I think it's a little bit late in the talk now. I have all these extra slides about D-wave, but I'm not going to go through them. I'm just going to the end of my talk here in case there's one helpful. Oh my goodness, my talk is long. In case there's one helpful on D-wave. So certainly okay, so let me pause on this one. I showed you that the kind of stuff we're trying to do in Oxford, by the way, we do superconducting qubits like the D-wave ones, but of a different variety here in Oxford as well. But the thing I mainly showed you was the ion trap. That lives in a vacuum, right? I said it needs to be in a vacuum, and hopefully you understood that that was to do with needing to isolate the qubits from the rest of the world. Now, if you build your qubits instead the way that D-wave and others do, which is as small superconducting elements where, for example, electrical charge can swirl one way or the other way around a loop, or you count how many charges are on a piece of metal, those make nice qubits as well, but they can't be in a vacuum because they're physically wired into other things. That's in their nature. So instead, you need to have superconducting devices. That means you're cold already, but actually you want to go as cold as you can in order to, essentially, similar reasons to our vacuum, which is to isolate the qubits from the noise in the environment around them. So if you want to talk more about D-wave, please hang around afterwards, but I suspect with the time ticking on, I can't do a what is D-wave thing right now. It is I'll say this, it's not in practice an approach to universal quantum computing. It's, however, a specialized device that may have very nice performance on certain narrow set of problems, which, however, are problems that are extremely important commercially, such as optimization, a bit like the traveling salesman thing that I showed you.
Yeah. Can you comment on how quantum computing might affect programs with recursive functions and their computability?
Okay, well, it's a large question to comment on how they affect programs in general. I guess I can make two remarks. Things that are not computable in the formal computer science sense are still not computable if you have a quantum computer. The thing to remember is that we know the equations that govern a quantum system, and we can simulate those equations using a conventional machine. The only thing that stops us is it gets just too hard for those computers. But I mentioned that this machine on my tape, on the desk here, I've had it running, simulating 24 or 5 qubits, I think, and the machine that we have in Oxford that we brought in specially for this will be doing about 35 qubits, and then it gets harder and harder. But not for a foundational reason, just because the task of simulating these things just goes off the chart, right? But that doesn't change the questions of what is or is not computable. And let me take this opportunity to throw another thing out here. The main reason that it's important to get small quantum computers working is so that guys who are not physicists but are from a programming background or just interested in this sort of thing can have a go, right? What we've had to do so far is imagine one of these machines existing, and I say the word we in the community sense, and try and figure out things it would be able to do without being allowed to have a go, right? And that's really hard. And that's why we don't have very many concrete examples. We have the factoring algorithm. We have things like simulating chemistry, where we're very optimistic that the machine will be a revolutionary device. But really, we just need one, even if it's a small one, so that people can have a go. And part of the challenge then in building this machine is not just to build it, but to put interfaces onto it that allow people who are not physicists to be able to understand what it is they're doing and just produce programs and try them out. Even some of the profound advances in, say, deep learning, which are now revolutionizing many things in conventional computing. Jeff Hinton, I was at a talk last year where he was explaining that his insights that really unlocked areas of that just came from having a go. You know, he had an idea and he thought that probably won't work, but I'll try it, and it worked fantastically. And that's what we need to get to, the era of the early machine that the enthusiasts can try.
So we'll have a question over here and then back in the middle.
Thank you for this very informative lecture. I was just wondering, will we still need logic gates with quantum computing?
Okay, good question. Well, the kind of machine that we're trying to build in Oxford and that most academics are working on is exactly built on logic gates. They're just the quantum generalization of the logic gates that you know about from conventional computing. So in conventional computing, you might have AND gates and OR gates and NOT gates, and you know how to implement those technologically. And you also know that those guys are a set of building blocks from which you can build any algorithm. This is this universality. If someone's got a machine that can do AND gates and NOT gates, and you're allowed to set, you know, how it does them, you'll be able to do a general purpose problem. That's the same sense, exactly the same sense in which our quantum computer will be universal. It just has a generalization. It's not even hard to understand. You replace the NOT gate, which flips a 0 to a 1 and a 1 to a 0 in conventional computing, with the general ability to rotate a qubit, because the qubit is this richer object, and you replace the, let's say, the AND gate with an object called a control NOT, which is just 2 qubits come in, and one of them gets flipped if the other one is in state 1, but not if it's in state 0. Very simple. And those are our logic gates for the quantum world. The D-Wave approach, however, doesn't use the logic gates. It works in a fundamentally different way, which at once limits it, but also allows it to make rapid progress when these universal machines are not quite ready.
This is a question from someone who maybe thinks of computing in a very classical way. So you talked about the Q2020 and you're looking for problems that it might be able to solve.
Yep.
Given I have a problem, if I got it right, something that is like a program that can be like parallelized or beneficial. And I have my idea of my program. I think that thing that it is very mysterious to me. How would what would be the compiler? What is the equivalent? How do I...
Excellent question. So I think I understand the question. So, I mean, let me answer it in 2 very quick ways. On the one hand, there is no compiler that you can access at the moment, but people are developing that. So people are working on exactly that. And at the moment, the compilers will compile against a simulator of a quantum computer. A bit like if you develop software for the iPhone and you don't want to have to keep loading it onto your iPhone, you actually have a simulator of the iPhone that runs on your computer and shows you roughly what it will look like. So we already have people working towards compilers that will take your program, turn it into low-level processes, and then because we haven't got the quantum computer to run it on yet, run it on a simulator of the quantum computer, and that's then ready to plug into this kind of machine when it becomes available. And I was going to make a second remark. Yeah, compilers. Oh, well, more broadly, if someone has a hard problem, I mean, it needs to be something that conventional computers struggle with. I should stress, quantum computers won't speed up the things that conventional computers already find easy, okay? In fact, qubits are slower and harder to manipulate, so it would be even the wrong solution for certain kinds of problem. It's the things that conventional computers fail on that we're really targeting for the quantum computer. Now, if you have a task that you think, oh, I wonder if a quantum computer would be able to make my thing go faster. Maybe it's a problem that's come up in your research, or maybe you're a bank and you're worrying about portfolio optimization or something, or whatever, then now what I would say is come and talk to us, or come and talk to one of the other big efforts on quantum computing, because we specifically have research opportunities which are trying to see how to map real-world problems onto these machines, especially the first-generation ones.
So we've got this gentleman here and then that gentleman here, and I think we might be
I'm getting a bit knackered. So.
This might be
This
might be a bit of a stupid question, but I was reading recently that in the brain, metal ions are actually used, they think, to store memories. And this sounds a bit like the ion trap. So I was just wondering if you've been talking to people like Roger Penrose here that think that the brain might be in some way quantum, or if that's something you've looked into. So
I should say, first of all, it's certainly not a stupid question. Speculative question, but not a stupid question. So the question, my quick answer is I think no for that particular thing. But if I generalize your question a little bit, the question of whether these interesting quantum effects, which seem to be there in nature for us to harness if we're clever enough, could they have been harnessed by nature, as in Mother Nature, living systems? Could it be that living systems actually have some amount of this quantum funkiness going on inside them, making them good at what they do? A provocative question would be whether that happens in the brain. I think I would say there isn't clear evidence that that's the case, but let me come down to a couple of things that are less ambitious. There's research, theoretical and experimental, that suggests that quantum effects may be significant in a sense that humans don't have or barely have, but other organisms do, which is a magnetic sense of direction. So that includes birds like the European robin that migrate huge distances. We try and understand that sense organ, which is challenging because we don't have it even, and it seems that that may rely to some extent on quantum coherence. That's a sort of controversial area. And then perhaps even more important is the area of photosynthesis, which is the way that, of course, plants harvest light in order to convert it into chemical energy. That is an enormously efficient process, and we would like to understand it better, both because it's something we should understand, and also because there's the possibility that we might be able to take insights there and build our own better solutions. And there's, again, considerable evidence that the process of photosynthesis involves quantum coherent propagation of energy and interference effects, and that's the core of why the plants are able to do it so efficiently. So, and in fact, exploring those extremely provocative questions, which could really provide an alternative route to some of the things I've been describing, is the core of the Martin School project. So I've given you this overarching view of things, but if you want to think about quantum plus biology, whether it's there, whether we can harness it, that's exactly what the Martin School is doing. Oh, sorry, the mic's over here, so who has the mic?
I wanted to ask, will there be sort of mainstream or consumer, let's say, technologies that are based on quantum computing, let's say some decades down the line?
Yeah, let me answer that quickly. So it depends what you mean. So sensors, I think, will find their way into all sorts of kinds of gadgets. I have an anecdote that I've restricted myself from telling because I didn't want to mention the name of the guy, that was to do with a prototype gravity sensor and a politician, and whether or not there was a risk that his brain wouldn't trigger the sensor, but that's another story. The idea is that sensors certainly can be made compact in principle. If you go over to quantum computers and you say, will I ever have a phone, in like 2070 where we all have quantum computers in our phone? My instinct is to say probably not, because there's no need to. The kind of problems that they handle for you can easily be centralized in a facility which has, vacuum capabilities or low temperature. It can be made small, difficult to make it small enough to go in a phone, but no need. If we're all communicating over the internet, already if you ask Siri something, it gets sent to Apple and chewed up on Apple's big machine, and then the answer comes back. So there's really no reason that we would need the hard end, so to speak, of quantum technology to completely be in your hand, and yet you'll still be using it in that scenario, just you won't have it in your house. And then perhaps this, yes.
Yeah, we've got time for one more.
Just to take that question on one stage further, is anyone looking really at the cultural implications of how it might change society, the world, etc., our inhabitation of the biosphere, if you started to fill rooms like this with machines like that?
Yeah, it's a good question. Well, so it's the impact of these technologies on society is, of course, a very broad question. I've already touched on the implications on the security side. The implications of having a computer that can solve problems even more efficiently than our current ones are intriguing. But your questions seem to draw towards particularly the idea that these machines will be big. So the good news is that when we get these things fully working, the amount of, let's say, electrical consumption that you need to solve a given problem is less than you would if you were going at it conventionally. So the way you go at these things conventionally is you buy a heck of a lot of conventional computers, and you fill a server center, which is like an enormous room, with like rows going to vanishing point in either direction, and that thing consumes tons of power. There's reason to expect that if we were taking those problems, in fact, I think the first thing that the big machines will be able to do is things that conventional computers can do, but the quantum computer will do it just with a smaller amount of hardware, and that's commercially in your interest because then you don't have to pay the electricity bill. And so I think it's good news in that respect. And if I was going to waive the sort of the environment as opposed to society, which is a sort of more complex question, I think that also in terms of modeling some of the problems that come from understanding the environment and sort of global change and so on, is also in this category of hard problems that we may find can be accelerated with these machines. So I think it's generally an optimistic note that I'd like to chime there.
Well, before we thank Simon, I obviously do want to flag up what's coming up next week we've got Mike Osborne, who's going to talk about machine learning. So I think it follows on quite nicely from what we've had today, and I really would urge you to come to that. Mike's a wonderful speaker as well, so I think you'll enjoy that. And then the last 3 will be on new and novel technologies for vaccine delivery, driverless vehicles, and then predicting technological progress. So we've got 4 more really great seminars coming up in the series. So do look online. If you're new, I do see some faces today that I think are new faces. Please do have a look on our website. We have so many events coming up. I can't do justice to them today. So thank you so much, Simon. That was a brilliant talk.